Okay, YouTube, this is my second video on solving for unknowns using exponential logarithmic growth models. And in this video, we're going to focus on investments and compounding interest. So we'd say, how long would it take an investment of $1,000 to double? And this is often a question we like to look at. How long does it take to double something? And we're going to change the stipulations here, but it looks like we have an 8% interest rate. So we have our rate here in this first situation, and it's compounded monthly. So in terms of n, we're going to have 12 times a year. And we would try to find out the length of time it will take for this to double. So because we have a compounding monthly, we have n times per year, we have our amount A is equal to our principal times the quantity 1 plus r over n to the nt. So the things that we're actually aware of here, we have an initial investment here is 1,000. And we also know that our rate is 8%. I'm going to go ahead and write that as a decimal, 0.08. And I know that my n value here is 12. The only things that we don't know are the amount here and the time. And so when you look at this, it says how long will it take an investment to, to double if it's $1,000. The real question we're trying to find here is what is our time? We're looking for time. So what this means is we're actually going to have to know everything else except for the time to find the time, or solve for time in general with respect to A. But the thing here is, because we asked the question how long does it take for this to double, we have to just kind of be sharp and figure out that we mean that A is going to be 2,000, okay? So what we'll do is we'll plug in this 2,000 for our A, write in our principal, which is 1,000, times the quantity 1 plus now our rate, which is 8% over n, which is 12 times a year, and this is to the 12t power. So you can see in all of this jumbled stuff right here, really the thing that we're looking for is the t that's up here in the exponent. So in order to solve for this, we're going to solve this just like we would any exponential expression. We would try maybe the one-to-one property first, but we'll see that this is a little bit more complex. So what we're going to do is we're actually going to isolate the base of the exponent and rewrite this logarithmically. So the first thing we're going to do is divide both sides by this 1,000 that you see here. So when we divide both sides by this 1,000, we just get left with 2 on the left. And on the right side, we have this 1 plus 0.08 over 12, and this is to the 12t. Now, I'm not a big fan of writing log base this of both sides, but we'll rewrite this logarithmically. The first thing I want to do though is all of this stuff on the inside here, I want to simplify it. So I really have some decimal in here. This is 1 plus, and in parentheses is 0.08 divided by 12. We would get this decimal right here about 1.006 repeating. So what we're going to do is we're going to rewrite this logarithmically, where this is our base, and I can say log base 1.006 repeating 6. This has turned into 2, and it does so by taking it to the power of 12 times t. So now at this point we could just divide everything by 12, and this is repeating, not a negative right there. So what we end up with is a time that is equal to log base 1.006 of 2, and this is all over 12. That's going to be our time. So let's actually figure out what the time would be on this now that we have the algebra done. So because I have log base 1.006 repeating, what I'm going to have to do is change a base formula. So the first thing I'll do is I'll take ln of 2 over ln of 1.006. So we have ln 2 divided by ln 1.006, and I get this numerator value here, and then I'm going to divide this by 12. And I get about 9.66 years here. So approximately, and this is in years, about 9.66 years would be approximately the length of time it would take under these conditions for it to double. So now in this second example, which I like much better, the reason why is because it's compounded continuously. We're going to be using our other growth model, which is that amount equals principal times the natural base to the RT power. So we have the same interest rate. We want to find out how long it's going to take for this to double. So again, our amount here is 2,000. Our principal investment was 1,000. So we have e to the rate times time, where our rate is 0.08, and then time is left general. So again, we're going to isolate the base on the right side there. Get that e to the power of by itself. So we have 2 equals e to the power of 0.08t. And the reason why I like this a lot better is because we can rewrite this a lot more easily without getting this big decimal 1.006. So we say log base what? Well, our base here on this exponential thing is e, so the base here is e. And all of this on the right side here turns into 2. So log base e of 2 is equal to 0.08t. And honestly, we should write this as ln of 2 is equal to 0.08t. So now we're going to divide both sides by this 0.08 and get your calculators ready. We're going to find a time here. But if we were compounding continuously and not just monthly, we'd see that it probably should take just a little bit less time because continuously compounding interest is just so continuous. So we say looking at this, about 8.66 years. 8.66 years, and that is actually a whole year shorter. So yeah, basically we want to highlight that we're plugging in known values and searching for unknown values, and it's very likely that you're going to have to solve this using properties of logarithms or properties of exponents. Cheers.